Hey everyone, welcome back, and thank you for joining us again in our next discussion of statistics. Heading into our first objective then, we need to be able to compute the standard error. But before we discuss that, the true linear relation between the explanatory variable x and the response variable y is given by y equals a beta 1x plus a beta naught. Now we say this because b sub 1 and b naught are the unbiased estimates of beta sub 1 and beta naught, so b sub 1 and b naught are statistics. Their values will vary from sample to sample. So there's a sampling distribution associated with each of them. We use this sampling distribution to conduct inference on b sub 1 and b naught. Now the standard error of the estimate, s sub e, is the unbiased estimate of sigma. So we have an estimate of the slope in b sub 1, we have an estimate of the y-intercept in b naught, and now we have an estimate of sigma in s sub e. And sigma would be the standard deviation of the response variable y for any given value of x. Notice that x and y are still connected here. We find s sub e by taking the square root of the sum of the squared residuals and then dividing by n minus 2. And note that typically we just call s sub e the standard error as opposed to the full name the standard error of the estimate. Now to compute the standard error, we're going to enter our data into L1, L2. We're going to find our least squares regression line using the linreg ax plus b function like we've done before, and then we're going to compute the standard error by inputting the formula into our calculator. This also means that we need to be able to find the sum of the squared residuals, since that's what the formula calls for. But we'll review that with our example. Heading into our example then, the data shown are based on a study for drilling rock. We've seen this example before when we discussed linear correlation coefficients. The researchers wanted to determine whether the time it takes to drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So again, the depth at which the drilling begins is the explanatory variable x, and the time to drill 5 feet is the response variable y. Part A asks, what are the unbiased estimates of beta sub 1 and beta naught? Well, we just need to remember the vocabulary. The unbiased estimate of beta sub 1 is b sub 1, which is our slope in a linear regression model. And beta naught has an unbiased estimate that is b naught. So we just need to find b sub 1 and b naught. So that means in our calculators, we're going to go do a linreg ax plus b again. And before we head over to the calculator, let's make sure we put all our x values into L1, and we're going to put all our y values into L2. Heading over to our calculator then, I'm going to hit stat and edit, and I put my data into L1 and L2 already, which means I'm going to hit stat again, arrow over to calc like we've done before, and we're looking for the linreg ax plus b function. Hitting enter, I'm going linreg of an L1, L2, and that gives us our results for A and B, which is what we were looking for. Heading back to the notes then, from our calculator we found A to be approximately 0.0116, and we found B to be approximately 5.5273, which means we have our unbiased estimates where beta 1 is equal to A, and that's approximately our 0.0116, and beta naught, which would be our value of B from the calculator, of a 5.5273. Heading over to part B then, we're asked to compute the standard error, and this would be the standard error of our estimate. Well, from the notes we have our formula, which means we need to find the sum of the squared residuals. Well, reviewing a little bit, to find the sum of the squared residuals, we are going back to our calculator. First, we're going to generate the list of residuals into our L3, and you see the instructions on your notes. So heading over to our calculators one more time, I'm going to hit stat, and then edit, and we have our L1 and L2 already. Going over to L3 like we see in our notes, we want to define these as the resids. Now, since we just ran the linreg ax plus b function, that means our list of residuals has already been created for us. So to define L3 as our residuals, I just need to access that list. I'm going to hit second, and then list, arrow up to skip to the bottom, and there's my list of residuals. Hitting enter, we now have L3 defined as the residuals, but remember we want to square those, so I'm going to go ahead and hit squared. Hitting enter, it populates our L3, and we have our list of our squared residuals. Continuing with the notes, we want to find the sum of our L3 since we want the sum of the squared residuals. So I'm going to hit second and then quit just to get back to the home screen. Then I'm going second and list, arrowing over to math, and we see option number 5 is sum. Hitting enter on sum, I want the sum of L3 like we said, and that means I end up with the sum of my squared residuals at approximately 2.7007. Heading back to the notes, just to repeat, we found the sum to be approximately 2.7007, and that means we can take that value, and that means we can go back to our formula and substitute our 2.7007 in for the sum of the squared residuals. Substituting our value of 12 for n as well, since we have 12 pairs of data. Remember, it's the pairs of data, not just each individual piece of data we have. And that means we get a standard error of approximately 0.5197. So here's the big question. When we're doing all this analysis, does the sample data provide sufficient evidence to support the claim that a linear relation exists between the two variables? If there's no linear relation between the response and explanatory variables, then the slope of the true regression line will be 0. Remember, a slope of 0 would mean that the information about the explanatory variable x does not change my guess for the value of the response variable y. That's where we see no relation and we see no pattern. So that means we're going to conduct a hypothesis test in order to answer this question. We want to test that two variables are related in a linear manner, but first our requirements need to be met, where the sample needs to be obtained using simple random sampling. The residuals need to be normally distributed. If it's not stated that the population is normal, we need to do a normal probability plot on the residuals, and that's going to be a new part for us. And finally, the residuals need to have constant error variance, where we will do a residual plot to verify this. Heading into the steps for the hypothesis test. First, of course, is to determine the null and alternative hypotheses. Notice that the hypotheses are based on beta sub 1, which would be the slope of our linear regression model. Next, we're going to select the level of significance alpha, which is again typically given to us by the problem. Then we'll calculate the test statistic t naught by taking b sub 1 and dividing it by s sub b sub 1. Now careful here, s sub b sub 1 would be the standard error of the estimate divided by s sub x times the square root of n minus 1, and that is s sub b sub 1 is the sample standard deviation of b sub 1. And once we have our test statistic t naught, we will use the tcdf function to find the p-value of our test. Notice though that when we use the tcdf function, we have to make sure we input n minus 2 degrees of freedom as opposed to n minus 1. Like we've done in the past, we have to draw the curve, and when we find that p-value, remember to use the tcdf function. We go lower bound, upper bound, and then our degrees of freedom. And just to repeat, we need to use n minus 2 degrees of freedom. Once we have our p-value, we'll be able to state the conclusion, and we know that if the p-value is less than alpha, we get to reject the null hypothesis. Heading into our example then, we're still presented with the drilling data. Remember, we have our x values in L1 and our y values in L2. And first we're asked to determine whether the residuals are normally distributed and have constant error variance. And this is us making sure that we have the requirements met to conduct a hypothesis test on the slope. So first let's check for the normal distribution, but remember we're going to check to see if the residuals are normally distributed, so we're going to make a normal probability plot of the residuals. Heading over to our calculators then, reviewing how to make a normal probability plot, I'm going to hit second and then stat plot, and now I'm going into plot 1. When we're in plot 1, we want to select our normal probability plot, which is over here at the end on my calculator. And our data list, instead of L1, we need to make our residuals. So I'm going to go second and then list like we've done before. I'm going to hit the up arrow to skip to the bottom, and there's our list of residuals. Which means we want the data axis to still be X. Any mark works, so let's go ahead and hit zoom, and then option number 9 for zoom stat. There's our normal probability plot. It does appear to be approximately linear, which means we can say that it does appear the residuals are normally distributed. So we can go ahead and check off the requirement that is the normal distribution of the residuals. Next we'll check to make sure we have constant error variance, which means we're heading back over to our calculator. I'm going to hit second and then stat plot once more, and this time instead of doing a normal probability plot, we want a scatter plot. Highlighting the scatter plot option, my X list I still want to be L1 now because we want that to be our data. But the Y list we want to be our residuals, and mine's already set. Any mark still works, so now I'm going to go zoom, and then option number 9 one more time for our zoom stat. We end up with our residual plot, and since we have no pattern, it looks like we're all set, and we've got constant error variance. And that means we can check that off our list, and our requirements have been met. Moving to part B then, since we found out that our residuals are normally distributed, we're going to test the claim that there's a linear relation between the drill depth and the drill time at the alpha equal to a 0.05 level of significance using our drilling data. So heading into our hypothesis test, we have our requirements met already, which is what we did in part A. So now let's state the null and alternative hypotheses first. Our null hypothesis is beta sub 1 equal to 0, and the alternative hypothesis would be beta sub 1 not equal to 0. Now this is not equal to because we're asked to test the claim that there is a linear relation. If we were asked to test the claim that there's a positive relation, then that would be beta sub 1 greater than 0. Similarly, if we were asked to test the claim that there is a negative relation, that would be our beta sub 1 less than 0. And next would be to find our test statistic, which means we need to find b sub 1, which we previously got from our calculator. We need s sub e, the standard error, which we found previously. And then s sub x would be the sample standard deviation of our x values. Well, as previously stated, from our linreg ax plus b function, we previously found b sub 1 to be approximately 0.0116. And then in a previous example, we found s sub b to be approximately 0.5197, and that just leaves s sub x. Well, like we've done a bunch of times now, we can run the 2var stats function in our calculator to find s sub x, where we would do 2var stats L1, L2, or a 1var stats of just L1, and we get s sub x to be approximately 52.2287. So I'm going to substitute my value of 0.0116 for my b sub 1, substituting 0.5197 for our standard error s sub e, substituting s sub x with our 52.2287, and then one more time our sample size would be n, and we've got 12 pairs of data, which means we end up with a test statistic t0 of approximately 3.87. So drawing our t-distribution and putting our t0 on the map, remember it's a two-tailed test, so we've got t0 of a 3.87, and we're also going to account for the negative side of that, so we've got a negative 3.87. And that means to find the p-value, we're going to find the area under the tails, and our p-value would be 2 times our tcdf function, where I'm taking the positive end, our 3.87 would be my lower limit, positive infinity my upper limit, and our degrees of freedom would be 10, making sure we're careful with that because we have to do an n minus 2 there. That gives us a p-value of approximately 0.0031. Comparing that to our alpha of a 0.05, we've got a p-value that is less than alpha, which means we know we get to reject the null hypothesis. And that means our conclusion would be that there is sufficient evidence at the alpha equal to a 0.05 level of significance to conclude that a linear relation exists between the drill depth and the drill time. Well, as previously stated, we can use our calculators to help us out with these hypothesis tests. To conduct the hypothesis test from the previous example, we're going to use the linreg t-test option. So heading over to my calculator, you see the steps in your notes. We're going to go stat and then head over to tests. And I'm going to hit the up arrow to skip down to the bottom. See option F here, we've got linreg t-test. Hitting enter takes us into the details of the test. We have all our x values in L1, our y values are in L2, so we're all set with our lists. And we were conducting a two-tailed test, so we're all set with the alternative hypothesis. We're going to leave this reg EQ blank, and the frequency is just 1. Hitting enter on calculate, we get our test results. Notice with this test, it gives us a bunch of information. It gives us A and B here, but that can be the most confusing part. Make sure we're careful. We've been using linreg AX plus B, while the linreg t-test function uses A plus BX. So just make sure we're a bit careful here if we ever use A and B as well. Because with this function, A is representing our y-intercept, and B is representing our slope, which is opposite as compared to our linreg AX plus B function. We get our test statistic of 3 and change, and it's slightly different than what we did by hand, but only a result of rounding error. And our p-value we got very similar to what we did by hand as well. Our degrees of freedom was 10, and what really makes us happy is this value of s represents the standard error. That's s sub e, which we found using the squared residuals, etc., and it's given to us in the linreg t-test function. If I hit my down arrow, it also gives me r, the linear correlation coefficient, and it gives me r squared, which would be our coefficient of determination. So the linreg t-test definitely gives us a lot of information. Well, heading back to the notes just to make sure we're clear. From the calculator, we got a test statistic of a 3.85, which is the value for t in the calculator. By hand, we got a 3.87, but nothing to worry about there as a result of rounding. And a p-value of a 0.003, just like we did by hand. And we're all set with our hypothesis test. And thank you again for joining us.